Okay. Let's erase not everything, only this part here, maybe. For now. So so we so boundary operators form the so-called chain complex. Form a chain complex. A chain complex is just anything that satisfies. So diagrammatically is set, a collection of modules or vector spaces that such that the square of the operators that so the composition of operators is 0. We have C d m by dd goes to cd minus 1 m, and this is dd minus 1 to c1. This is d2 and this is d1. And this is c0 and dp plus 1 composed with dp plus 2 is 0. So this is chain complex property. Now the dual space, so these are formal combination of chains, and the dual space will be functions on that formal linear combinations, linear functions, which is equivalent to giving a number to each cell. And this has, if the cell represents something cleaving on a cell represents a physical property, giving a value to that cell will constitute a cochain on all cells. So physical properties will be naturally represented by cochains. Okay, in fact, we will represent by discrete forms, but they are cochains on a extended complex. So this is for later, just to define. So this is from before. I'm just using the same matrix for example, for an example. So let M with epsilon be a combinatorial mesh with orientations, with relative orientations. Let me give some, I will use this kind of notation. So let's give some abbreviation. So C M W R O. Combinatorial mesh with relative orientations. And first of all, for defining the dual space, we don't need orientations, but for P in 0 to the dimension of M, define the space of Cochains as the space of Cochains C P of M as the dual linear dual from R linear from R linear dual of C subscript M. So CPM is CPM dual space. And C upper bullet M is the direct sum of C P of M. So this is space of Cochains. Usually, no, very often we work separately with different dimensions, but sometimes we may need to have them all together. And so then define the okay. So we have basis. So dual. So zero cochains are spanned. So P cochains are spanned by the following. So for P equals 0, we have N0, N1, and so forth. I don't know, I usually use start with 0, the indices. P equals 1 by E0, E1, and so on. P equals 2. So these are the dual. F1, F0, F1, and so on. So these are dual of N0, N1, dual bases. E0, E1, F0, F1, and V0, V1. So okay. The coboundary operator coboundary operators delta P from C upper index P M to C upper index P plus 1 M. P is from 0 to D minus 1. Okay, here this is the dimension of M, of course. Are the dual of D P plus 1. So BP star is the dual of P1. And so what does mean? Let me recall. So if sigma is a picochain, then delta P of sigma is sigma composed with partial P plus 1. And this is a linear function C P plus 1 M, which is a linear function on the cell space of P cochains. And matrices, so in matrix terms, the matrix of P delta P is the transpose of delta P, partial P plus 1. So it is the transpose of this matrix. I proved such a theorem long before. In Algebraic. So this is a particular case. So for example, and we have d P plus 1 composed delta P composed with plus 1 composed with delta P equals 0. So this is Cochain complex property. So we have C0M delta 0 C1M delta 1 to C D minus 1 M. Oh, sorry. This is delta D minus 2 C D minus 1 M, and delta D minus 1 goes to C D of M. And any two after each other gives 0. This is Cochain. So here we have in the example from before. We have that delta 0 will be this matrix here, but transposed. So we will have edges. So, edges. Sorry, nodes here. And edges. So I have -1. What I did? I'm so confused. E0, E1, E2, E3, and 0, and 1, and 2. Okay. So we have -1, -1, 0, 0, 1, 0, -1, -1, and then 0, 1, 1, 1, and delta 1 will be E0, Oh, sorry. F0, F1, and then E0, E1, E2, E3. 1 minus 1, 1, 0, 0, 0 minus 1, 1. So I have this matrix. And let's do some computation, for example, not with a matrix, but with operators. So if we have sigma is a 0 form, then delta zeros and take some. So delta sigma applied at some one, for example, E1 will be sigma composed with delta, so this is delta 0. Sigma composed with delta 1 of E1. And so this will be delta 1 of E1 is N2 minus N0. So this will be sigma of N2 minus sigma of N0. And if rho is a one form, delta 1 sigma of, let's say, F0 is a rho composed with delta partial 2 of F0, which is, so this was E0 minus E1 plus E2. So this will be rho E0 minus rho E0 minus rho E1 plus rho of E2. And this is how the here is also. So this is the two Cochains given by this formula for F0. So a rho is a one Cochain, the result is a two Cochain, but when applied at the cell, it uses not the value at the cell, but at the cell boundary with sizes, with the respective signs. Okay. So the boundary operator on meshes is a straightforward generalization of the boundary operator on, not the bound, but the boundary on manifold. So in the manifold theory, we have the topological boundary, but we have to be careful with orientations. And it can be explained by these relative orientations how to do that. But it's more interesting how to relate the coboundary operator with smooth differential geometry. And this is given by the Rham map. So we have the following definition. And the Rham map is not used if you do a explicitly discrete theory, but it's used when we discretize a continuum model, for example. So let X be a smooth manifold. D is the dimension of X, and and be a mesh combinatorial mesh with embedding in X, with embedding on X. So we fix some embedding. And P is from 0 to P. The Rham map, called after George Rham. So this is RP from P forms, RP from P forms to on X to Cochains in M is defined as RP. So we take some for omega, and we have to apply it to a cochain, to a cell C is the integral over some embedding. Let's go with phi, and we apply it on the embedding, the form. So here omega is a P form and C is a P chain, a P cell. This is a P chain, a P cell. This is in MP. This is for basis chains. It can be extended by linearity. So extended by linearity. Extended by linearity to all P chains. Let me give example. So let's say we have the following. I will do only 1D example because it's easier. So we have 0, 1, 2. So this is X. This is X is the interval from 0 to 1, and this is so okay. X is 0, 2, maybe. And yeah, M is this mesh, so M is this is and 0 and 1 and 2 is 0 is 1. So M is E0, E1, and 0 and 1 and 2. This mesh here. Okay. And let's take omega is a one form, so this is f times dx. So let's say omega is first, okay, p equals 0. and omega is, let's say, is f, is omega is a function. So this is a function. So omega is from x to r. Then r0 omega at, let's say, ni will be the integral p of ni. Okay, I forgot to say that p maps, so no, p of ni equals I and phi of ei. So the point is mapped to the number e, the point, and the hei is mapped to the that connects them. So this is I plus 1, this interval here. So we have the Rham map at this omega applied at cell is the integral, but integral over of a function is function applied at this. So this is omega of fi, which is omega of I. Now, so we just mapped omega to a discrete function that on the point 0 maps the on n0 maps the real number 0, n1 maps the real number 1, on n2 maps the real number 2. So we can write this as r0 omega is n omega I times n upper 0 plus this is omega 0 plus omega 1 and 1 plus omega 2 and 2. And that's a bit more interesting for 1. And that's a bit more interesting for 1 equals 1. Here omega is, let's call it eta. So eta is f times dx, and f is function from x to r, a small function. Then r1 of eta at point at hei is the integral of phi of ei of eta. So this is integral from, in this particular case, not always, but in this mesh, e to e plus 1 of f x dx. And so r1 of eta is the cochain given as follows. So this is integral from 0 to 1 fx dx times e0 plus integral from 1 to 2 fx dx of e upper 1. So this is this cochain here. So the Rham map allows us to discretize forms into cochains. We just need to integrate over the cells, and this will be the coefficients. So a cochain is given something times this basis cochain plus something times this basis cochain, and the coefficient is an integral over the image of that cell. So this is an abstract complex, but here it's embedded to the interval 0 to 2. Okay. Now we have the following theorem, proposition, doesn't matter. This is equivalent to Stokes theorem. Cartan. Stokes Cartan. Let's call it Cartan's theorem. So on a smooth manifold X with embedded mesh M, and P is from 0 to dimension of X. We have that R E composed with D RP plus 1 composed with dP is delta P composed with RP. So R is a Cochain map, and this is 2 minus 1. So we have the following diagram. We have omega 0 to omega d. So this is the dimension. And we have d0 to d minus 1. And at the bottom we have the mesh. The mesh. The delta 0, delta d minus 1. And they are connected by the Rham map. So from L0 or R0 to from R0 to RD. And we have here as well some maps. And this commute. So let me give example in 3D to be. So for d equals 3, we have omega 0, omega 1, omega 2, omega 3. D delta, this is d0, d1, d2, and we have d2, and we have r0, r1, r2, r3. Here we have x. Sorry. In the paper, I have M for manifold and curved M for a mesh, but here it will be very ugly. So C1 of M, C2, C1 of C0, C1, C2, and C3. Delta 0, delta 1, delta 2. So this diagram is commutative. So if I go there or there, it is 0, it is the same, or go here and go here. And so what people in numerical analysis community say that we have some kind of compatible discretization. If we discretize from something continuous to something discrete, the discretization and the operators are compatible. What? Okay. So example of a map that discretizes beautifully is the trace map. So yeah, I'll finish now. Let M be a combinatorial mesh. L be a submesh of M. And then so it's a mesh that is a subset of M. The trace map trace from trace P from CP M to CP L is defined by I suppose as trace P of some sigma at cell C is sigma of C. Maybe where sigma is P form and C is a chain. So we have a subset, and any cell in L is a cell in M. And we applied the trace by it's like restriction. And so the good fact is that the discrete trace it corresponds to the continuous trace, smooth trace. So we also have, it can be given as the following diagram. So if I have omega P x m to omega P x L, so I have two manifolds, and then I have trace smooth, and then I have the Rham map RP to omega P m to omega P x. This is the Rham map on M, and this is on L. This is CP. Yeah. And this is trace P discrete. So we have the whole following commutative diagram. Yeah, so the trace is used to define boundary conditions, the smooth trace, and the discrete trace can be literally substituted for the same boundary conditions. And this was very hard if you use vector calculus. You don't know how to describe this inner product with the outward pointing boundary, a normal. But here with the traces, it's very direct. Okay. Yeah.